MEC 2960, Lab 5, Flexure Representation Report. My name is Nick Marjano.
My name is Jacob Hoffman.
I'm Chris Liska.
I'm Logan Freeman.
Our objective for this lab, it was to analyze Young's modulus and strain of a sample of acrylic using two bending tests. These are our four equations that we used. Sorry. The first equation was the strain equation. This equation relates to the measured output voltage ratio of the applied force and strain. It helps convert electrical readings from the strain gauge into measurable strain values. And the second equation was strain equation using radius. This gives a theoretical strain based on the beam's geometry, showing our thickness and how thickness and radius affects deformation. Young's modulus equation. We've been using this one. This equation calculates Young's modulus, a measure of material stiffness using beams deflection under a maximum load. And vertical displacement equation. This gives the vertical displacement of the beam at any point x, showing how the beam bends under a load depending on its length, stiffness, and moment of inertia.
Okay, so the first test involved taking a acrylic beam, sanding it, and then gluing and taping a strain gauge along the middle. And then the wires of the strain gauge were hooked up to a bench multimeter to read the voltage output. And then the beam was bent over a curved styrofoam surface with known diameter by hand. And 3 trials were performed to get a voltage output, which will be useful for later calculations. The second test was a 3-point bend test using a mechanical testing machine. The beam was measured, the same beam, 3 times with calipers, and then placed in the 3-point bend fixture. A camera was set up that had the displacement and force gauges of the machine in the picture, as well as the voltage output. And then a increasing force up to 10 pounds was applied onto the beam in the middle, opposite the side of the strain gauge, to obtain data for displacement, voltage output, and force. And that those values are also important for our later calculations.
Using the force and displacement values, we were able to make a bending plot using equation 4 as listed on the theory slide. This equation gave vertical displacement as a function of horizontal distance and used force, length, Young's modulus, and moment of inertia to accurately plot the vertical displacement at each point along the beam at maximum force. And you can see how the picture of the beam under strain relates to the bending plot graph. In part A, we used equation number 1 to have the voltage out and in and relate it to the strain. And we were able to calculate a strain value of 1.9 e to the negative 3. We compared this to the theoretical strain value found using equation 2, which used the thickness and the radius to get a theoretical strain of 5.83 e to the negative 3, which gave us a percent error of 67.28%. In part B, we used equation number 3 to calculate the Young's modulus, and that used inertia, force, displacement, and length, and that gave us a Young's modulus of 4.8 e to the 5th. And then we calculated stress and strain and plotted them against each other to get a stress strain graph, which gave us a slope of 6.22 e to the 5th. And we compared these both to a literary value. The Young's modulus calculated had a 1.3% error, and the Young's modulus slope value had a 34.1% error.
As the data showed, in part A, the percent error between our theoretical strain from equation 2 and our calculated strain from equation 1 was pretty high, 67%. We believe that this error came from the time when we measured the strain voltage, when we pressed the acrylic sample over the foam diameter. The idea is the foam diameter had some give So the voltage readings you got when you pushed would be highly variable. So even when they're averaged, you're going to get a pretty high difference from the theory. In part B, the calculated and graphed Young's modulus differed by 1.33 and 34% from the theoretical Young's modulus we got from the engineering toolbox online. These are pretty good values, all things considered. It definitely wasn't perfect. There were some errors. The biggest error we considered is the sensor alignment. When calculating stress in our stress versus strain graph, the bending moment above the z assumes that our x is in the exact center, L over 2. But our sensor is totally not in the center, L over 2. It's a little bit to the left, a little bit to the right, whatever it may be. So our strain values were based on a location not in the center, but our stress values were based on a location assuming it's the direct center. So I think that's where our larger percent error of 34% came from, most likely. And then the gluing of the sensor gauge, it's most likely that our gauge wasn't fully glued on the entire surface, so some parts weren't bending a total amount following the curve of the acrylic as it was being bent. All in all, with the setup we had using the displacement gauge, force gauge, and the voltage reader, the strain and Young's modulus of the sample were pretty accurately calculated. And we showed that the theory shown by the equations in the first slide, equations 1, 2, 3, and 4, were proved to be pretty effective because the test and those equations give us results that match pretty closely with the theoretical values we got from the theoretical strain equation, equation 2, and the theoretical value we got from the engineering toolbox. In the future, it might be best for part A with the foam diameter to make it a more rigid structure. So when you're pushing the multiple tests, it doesn't have such a variability. Or if we can't have a different structure to bend it over, it would be better to have a lot more than 3 trials so that the averaging out would do a lot more to lessen the variability between the trials. And in the case of B, it would be nice to have some sort of system to more reliably and accurately glue the sensor and position it in as close to the direct center of the acrylic sample as possible.
Thank you very much. That is our Lab 5 presentation.